All right, so firstly, I guess, thank you so much, I guess, for taking the time to join us today here. I know it's just after lunch, so I'll try to keep this a bit lively. I've got a demo in between there, so it's not all slides. But as you go through, if you're making any notes, about any questions you have, we can talk about any questions time. If you can't find time, then I'll give around my business cards. So let's chat, right? So make any questions you have are welcome as I go through these slides, okay? Thanks so much. Again, my name is Shashankara. I'm an applications development manager at CPFD Software. I have a PhD in mechanical engineering from Oregon State. I have been with CPFD for about 3 years. Prior to that, I've worked with ANSYS, and prior to that, I was working with Baker Hughes. So my industrial experience is mostly in oil and gas upstream applications, but in the last 3 years or so, I've been spending time with a lot of fluidized reactors. All right. With that, I'm not going to waste any time. I'm going to jump straight away into the topics I have lined up for today's talk. As I was, got in a sheet down there. Obviously, we have several application models, but keeping in with the theme of this talk here, we will focus on certain applications which are around hydrogen production. And I've got 3 of them lined up here. One is called the solvent enhanced steam methane reforming. So it is your regular steam methane reforming, but then we're adding solvents inside the reactor so we can capture CO2. Okay. The other is slightly different. It's called dry reforming of methane. So here you're actually reacting methane directly with CO2 that's been captured by other means, right? And you're producing syngas out of that. So another variance of how you would sort of produce hydrogen using CO2. Then this is quite interesting. I'm actually going to show you a simulation for a molten metal bubble column reactor. This is again to produce hydrogen, but in this particular application, we're going to focus mostly on the hydrodynamics, because that itself is quite complex enough. You have bubbles rising to molten metal bath, so you can imagine bubbles basically, growing in size, coalescing as they move out, right? So the physics involved is quite complicated. So I'll show an example of one of those there. Then we'll shift gears from hydrogen production, and then we'll go into decarbonization of direct reduced iron shaft furnace, right? We saw an excellent presentation this morning by POSCO. They were using Hyrex methodology, basically to decarbonize iron production. Here we look at some work we have done with molten industries in the US to actually reduce or basically reduce emissions from the production of iron ore. And lastly, I'll touch upon a CFD, which is the circulating fluidized bed combustor. Here, I'll show work where we are using basically coal to model this. But then this decarbonization via ammonia co-firing, this is not work done by us, but this is actually a publication that I found which was published by some authors up in Korea here, where they're actually combining ammonia co-firing with coal to capture some CO2 there. Okay, all right. Or to reduce CO2 gas emissions. Okay, with that, I'm just going to move straight into my topic, hydrogen production. Okay, so there are a bunch of words down here, but I guess the key aspect is this. As I was looking up at this topic, the Korean government has a mandate to reduce greenhouse gas emissions by about 40% by the year 2030. And then what this actually means is obviously you want a transition from carbon-intensive current hydrogen production methods to more sustainable ones, right? And you'll hear these terms called gray hydrogen, blue hydrogen, and green. Many of you, if you're working in this area, maybe you're quite familiar with it. But the best way to understand them is looking at this picture down here. The first one is called gray hydrogen. This is where the current production methodology, right? I guess about more than 70% of the world's hydrogen currently is produced by methane reforming. That can be quite carbon intensive. If you're using either coal, natural gas, biomethane, any other methodologies down there to produce hydrogen, that all falls under this CO2. You're not capturing, that all falls under gray hydrogen. You're not capturing your CO2. If in the same processes down there, if you were to modify them somehow, either to reduce CO2 production or capture it, that's when you move into this blue hydrogen, right? And that's where the immediate bang for buck is. You can continue to use your existing reforming reactors, but then can you modify them such that you can reduce greenhouse gas emissions, right? And then lastly, and this is where both my SESMR and DRM application models sit in, is under this blue hydrogen. Then the molten metal is where we would be producing hydrogen basically by bubbling methane or through a molten metal bath, right? And then You're not producing any CO2, you're basically splitting your carbon from your hydrogen molecule there. If the energy source for that comes from a renewable energy source, right, that's when it's purely green hydrogen. Okay? All right, so that's what I explained just briefly here. And Barracuda is actually very well positioned to be able to model these applications, as we'll see. The key in these, as you dig deep into them, the problems are quite complex. You basically have not only a complex multi-phase flow, just from the core flow point of view, but then you also have to couple them with reactions, essentially. And these reactions can happen on the particles of the discrete phase. These reactions can happen in the gas phase. And all of this is actually happening simultaneously at every time step. So you not only want to have these solvers which are able to simulate large-scale domains, right, like real-world domains, but being able to solve them stably as well. That's and that's where the power of NPPEG and Barracuda really shines out. Okay, so firstly, as I said, the first example I'm going to talk about is this SESMR. As I was mentioning, this is if you're producing just steam from your reactor, it's SMR, steam methane reforming. If I throw in some solvents in it, I can capture the CO2 before it leaves the reaction, right? Before it leaves the reactor. That's the idea here. This work is based on the paper published by Johnston now. Again, as I just mentioned, Barracuda virtual reactor solution is quite suited, captures multi-phase, couples physics with chemistry, and then you can see how you can actually, this works in action in your simulation, right? And the key, as everybody's been mentioning since this morning from Dr. Reddy, the idea is you're able to simulate stuff on a pilot scale, maybe on even a lab scale, validate that, and then once you feel confidence in your simulations, then maybe you can use that to scale up before you actually build your equipment. Okay, here is the domain. It's a simple lab scale domain, 1,000 millimeters in height, about 100 millimeters in diameter. The gas is injected from the bottom surface down here. This is the height of the initial bed size there. It's nickel-based catalyst. You have calcined dolomite as the solvent in the reactor. The gas is coming up at about 0.03 meters per second. And here is where all the chemistry of the reactions that we have implemented in this model, right? The first reaction is, the couple of reactions are your steam methane reforming. The methane reacting with water vapor, it's producing a bunch of CO2 along with hydrogen. And then if I can actually capture this CO2, which is what I'm doing in this discrete reaction, right? I've thrown in this calcium oxide, and that reacts with CO2, produces me calcium carbonate. So that's what makes it a carbon capturing methodology. The reason why I threw kinetics, I'm not going to go over them in detail, but for people to appreciate the fact that you can actually input very complex forms of reaction kinetics within Barracuda. They don't have to be in simple form for you to input. We provide you several default modules. If you cannot input them, we provide what is known as a user-defined expression down here. Again, the details are found in the post, you can look at them, but this entire discrete carbonation reaction has been implemented through a bunch of equations that I put in as a user-defined expression. All right. With that, let me show some results down here. Right? Best way to look at results, if I take one step back, here's the animation. I'm showing you mole fraction of CO2. This is the solvent-enhanced steam methane reforming here, and this is just a regular steam methane reforming. So as you go in time, you see that basically in the reforming process, you're producing CO2 in your regular reforming, whereas in your SESMR, you're actually capturing some of that CO2, right? For that based on a discrete reaction. And then sometimes, wherever possible, we try to compare some of our data with published literature. In this case, I'm comparing my dry mole fraction of hydrogen at the outlet of the reactors. I'm doing it both for my SMR, which is around the green curve, and the solvent-enhanced case on the red. The black dots are from Barracuda, and so you're seeing some, these are a mix of like simulation and experimental results. And we are looking at the mole fractions at different temperatures of the reactor. Okay? All right. Quickly moving on, dry reforming of methane, it's a very similar reactor. The idea though, the key difference is that steam is actually reacting with CO2 directly. It's not reacting with water vapor, okay? So everything else is pretty much the same. This work again is based out of a publication by Daejeon and others. Right, so a similar reactor, 30 centimeters in height, 2.8 centimeters diameter here. It's nickel-based catalyst. If you see the gas ratio I think coming in is methane, CO, and argon, 4:2 ratio on molar basis. Again, if you look at the set of reactions, they are different in this case. The first reaction is dry reforming of methane. You have methane reacting with CO2, and that's producing syngas here, hydrogen and CO. Okay, but then you also have reverse water gas shift reaction happening in this process. Ideally, you want to suppress this reverse water gas shift reaction as much as possible, because all the produced hydrogen, if not, then is going to be converted into CO and H2, and we don't want to do that. We want to keep the ratio of H2 more than CO, essentially, in this case. All right, and then again, the kinetics are there, some details about it that you can read up in the post. But again, I just want you to appreciate that these don't have to be very simple reaction steps to be implemented within that order. They can be complex. All right. Okay, so here I've got another animation playing. I am showing mole fractions of CO in this animation, and this is hydrogen. So with time, you will see that basically, again, the scale is the same. It goes from 0 to 0.3 in both of the examples. But you can see that with time, essentially, I'm producing more hydrogen than CO. So I've pushed my reaction pathways, and you do that by what temperature you're reacting this, the amount of catalyst present in the system, and so on. But I basically am getting the H2 to CO ratio greater than 1, which is what I want in a simulation like this. Okay, then we shift gears completely. This is for a lot of users here, whether they're using the software right now or plan to use it, when we talk about discrete phase system within MPPIC, it's not always solid particles. For us, discrete phase can be liquids, can be droplets and bubbles as well, other than particles. So that's something I want you to take away from today, is that when you think about Barracuda, it's not just gas and solid flows. Discrete phase can be a bubble in a liquid, or it could be a droplet going along with your gas as well. So this is one of those examples. As I said, the idea about producing hydrogen from a molten metal bubble column reactor, I'm just going to call it bubble column reactor. It's quite a mouthful to say that. So in a bubble column reactor, ideally you have a metal bath. Typically it's maybe thin. You're bubbling up methane as it moves up the molten metal. At that interface between the gas and the liquid, you will start having methane pyrolysis reactions happening. And then as it moves up, you get some hydrogen and then some solid carbon settles on top of that. That's the idea here. In this particular example, though, what I'm showing is, because there's not a lot of active literature, at least published, for methane pyrolysis in a metal bath. I took this example where they're injecting argon gas into a molten metal iron bath. There's a lot of published literature in this case, so that's what I've taken here. The key fact is, this reaction doesn't have any this simulation doesn't have any reactions in it. But even without it, it's quite useful because, as I said, right, the bubbles as they move up, they are coming closer together and they're growing in size. Sometimes they're breaking off as well. And so, as you can imagine, because the reactions are happening at that interface, that hydrodynamics of how the bubbles move up is quite important if you want to understand the reactor behavior. And that's what I'm trying to do in this particular simulation here. All right, so same, it's a simple rectangular bubble column here. Bubbles are being injected from a single point at the bottom down here. The top is the pressure outlet. The domain is completely filled with molten ferrous material at 1250 C. In this particular case, the animation I'm going to show you is for one injection rate of argon bubbles at 2.5 millimeter cube per second. Now here's the key difference, right? You will find a lot of studies and literature where people are using traditional CFD, like VOF models to simulate these, and they do a great job. But if you look at the computational time it takes to solve VOF, right, or a VOF simulation, the grid count is around 5 million cells to solve. In this particular paper by No, they use VOF and their grid size was 5 million cells. Whereas I was able to simulate this within Barracuda using about 11,000 cells. Right? That is significantly fast, and their whole runtime, the simulation time was a few seconds, 2 or 3 seconds, whereas I was able to simulate about 100 seconds within a matter of hours using Barracuda. And then again, you can essentially turn around more and more simulations as I've done in this work I'll show you in a second. Couple of important parameters, this may be for when you're actually setting up the model to think about is, because we're directly injecting bubbles down here, there are a couple of things. Firstly, in the simulation, we have to set what is known as a max bubble size limit, how big the bubble can grow, right? That typically is estimated from experimental work, and I've used that value from the works of Irons and Guthrie and No here. Similarly, coalescence factor, right? This tells you how probable are two bubbles that come close to each other to coalescence and form a bigger bubble. That is a factor we set up. Again, this is a value that one can obtain from experimental data, and I explained that how I've done in the post here. Lastly, obviously, because we're injecting bubbles directly, we need to know what is that inlet bubble diameter, right? And there's actually a lot of work published here where there's a relationship between the size of the bubble and the size of the nozzle through which you're injecting the gas. In this particular case, I used the work by Islam here, and so you can see a relation between the diameter of your nozzle and your departure bubble diameter. Okay. And then here's the simulation. These are basically argon bubbles as they move up the reactor. I am coloring the bubbles by their size. These are in microns. They go from about 5,000 to 16,000 microns. And again, you can see this. I mean, the inlet's bubble size is about 11 millimeters or 11,000. A couple of them, near the nozzle, they shear off because of high turbulence down there, and they become smaller in size. But essentially, as they move up, they grow in size. Okay. Then, not only that, what I ended up doing is I actually compared the results. Our results are in red dots down here. I am showing mean bubble diameter versus inlet flow rate to both some published experimental work and literature work on the paper. And again, you can see that across this flow rate range, we do a pretty good job. So you have to tune your coalescence factor and the maximum bubble size based on one of the flow rates. Once you do that, you can consistently use those values for other flow rates, as I've done in this work. And then I also compare the drag coefficient on the bubbles. Again, we do a great job considering how the grid counts we're using and how quickly we can solve these simulations. Okay. With that, I'm going to shift gears here slightly. I am actually going to open up our CPOV software webpage, and I'm actually going to show you the solvent-enhanced steam methane reforming application model. So bear with me for a second here. Okay, I'm going to go up on the website. So for those, if you're familiar, this is basically cpfdsoftware.com down here. This is our homepage. And we have application models under resources here. So if you go click resources, you'll see the segment for application models. If you see down here, there's a login button. And as of now, I have not logged into this web page, right? So this could be any user across the world or any browser, any internet browser who's just looking at a website. All of this is actually available for you to see without logging into our website. There are several of these application models. We'll touch upon a few. Peter was showing the cement calciner animations. We also have some application models for erosion, proper transport, and so on. But the one I'm going to focus on is this steam methane reforming, the example that I just showed. So let me click on this guy here, and it takes me into this overview page down here. So, just a few paragraphs which describe what this application model is about, what to expect when you start looking at this in some detail, right? And there are some short links here that take you directly into the post. If you already know where to go, just click on them. But all I have to do is click access model here, and that takes me actually into the main whole post for this SESMR. Again, I have not logged in yet, and I'll show you even without logging what can I see when I browse through this website. Firstly, introduction, right? So generally with most of these posts, you will find some high-level view of why this application model is relevant and why are we actually doing this. Some overview of published literature in this field. Once we do that, we briefly go over the model definition itself. So that basically means where have we obtained this particular model from, the dimensions of the model, the conditions, the flow conditions, and so on. So some of that information is given down here. We actually have a schematic for what the domain is. I just showed you this in my presentation. And then, because again, most of our users when are using the software, they're not just doing code flow. Almost all of them are using them with reactions. So you will find that in most of our posts, reaction kinetics are prominently displayed. We take a lot of time not only to put these reactions up there, we explain where we have gotten these reactions from, and we feel like there is any relevant information that we need to tell you, we actually explain that, right, in that particular post. So you can see all the different, the rates, the rate constants themselves, and some equilibrium constants and so on. Everything is written down here for you to take a look at. Once we are through that, then we start showing some results from the post. There are obviously so many different ways you can post-process the data. We show you some key highlights here. In this case, like I said, I was showing you CO2 mole fractions between an SMR and an SESMR case. We already looked at this guy. And then we have modeling instructions. Now, one thing we do is by the point you get to modeling instructions, you have some knowledge about using Barracuda. You have at least a basic user, right? So you at least know how to import in a CAD file, mesh it, and some basics. If not, we direct you towards a new user training. If you are really interested in it, it only takes you a few days to get used to software. The software is actually relatively very straightforward to learn compared to some other CMD software. So I would strongly encourage you to take a look at that. But here's where the key magic happens, right? You see this download support files? That's where actually we are providing you the setup itself, the model setup for Barracuda file, which contains this entire setup, right? And I'll show that in a second. But as I scroll down, some key steps about setting up this model that we think the user should know, because it's not only useful for this post, but subsequently in your work, you gain some knowledge from it and you can use it. That's the idea here, right? And that's it. Once you kind of go through some key steps here, we show you some post-processing. Again, in our previous examples or our previous application model posts, we would go step by step about how to post-process and obtain the images and the animations that I'm showing here, right? This is what we're explaining how to obtain. But I think going forward, what we're doing is we're also attaching layout files from TechProd. Essentially what it means is we already preset how the post-processing should look like. So you can just load that layout file and actually directly obtain the views. Okay. All right, oops, I clicked on it. Okay, so now let me go back to this access model that I was showing here. Here is where though support files, if I click on this, here is where it will actually ask me to log in. Now, if you're an existing user, you can log in and download the files. Even if you're not an existing user, you're interested in checking this out in the software, talk to us, email us. Maybe we can help you out getting the files and maybe even a trial license, right? If you have available for that. Okay. So here's where I'm going to log in. I'm going to log in just as a regular user. I'm not going to log in with my CPOD email. This is my regular email down here. I log in. And then that's it. It makes this zip file available from me. I'm going to click on this. I'm going to download it. It brings me up here. And I am actually going to head straight into my downloads folder. So this is the latest file I've downloaded. These are some of the other files that I'll talk about in a second. But this is the file I just downloaded. I'm going to right click on that. I'm going to say, open it up, extract the file. Oops, that did not work out. Right. Okay, so I've downloaded it, it's opened up, I've got the project down here. If I double click on this, you will see that we have actually made available the project file. And then if you're familiar with Barracuda, it actually creates a grid file. It has some .sif files, which are like your input conditions, your material properties. Everything was already set up for you, right? So let me just double click and open this guy here. Okay. So that brings up my folder. Okay, so this is actually our home GUI for Barracuda. If you are not familiar with it, it's actually got a tree structure here for project summary. So this is how a CMD user would go about setting up a simulation, right? A grid, materials, initial conditions, boundary conditions, chemistry, and then some post-processing. Right, so I'm going to show you briefly here. It's a simple cylindrical reactor. The only thing the user needs to do before running is generating a grid. because grid files in some cases can be large in size, so we don't do that. But all you have to do is click generate grid, it's done for you. Okay. So now we come in here, you look at global settings, it's an isothermal simulation, it is compressible in this particular case, but it doesn't have to be isothermal, we could have thermal simulations as well. We come to base materials, here is where we have defined all the base materials for you. Okay? And a lot of these base materials are already made available for you in Barracuda to take a look at. Then we move into particles domain. So here's where we define how our particle contact collision models are interacting with each other. What should be the close back volume fraction in this case is about 0.6. Right? So that information is given here. We move into particle species, and this is where the difference is. So I've got a couple of species in here, as I was saying, a nickel catalyst, and now it can have its own diameter, own PSD range here. Now I can either use the built-in, if all you know is a min and max the sizes of your particles, we use a normal distribution to build the PSD for you. We can do that. If you have your own PSD, for all reason, come to file and then just create your own PSD here, diameter and then the cumulative mass percentage for that. You can do that yourself if you have that information. And then the key is, this is for nickel catalyst, it's got a min 150 to 250, and if I come and look at my sorbent, it's got a different size range, right? So however number of species you can have, you can define your own PSDs for them. You're not restricted in that way at all. All right, with that, I think fluidization is straightforward. We just initialize at 300 C and then atmospheric pressure. The key is flow conditions here. It's very simple in this case. We just have a bottom plane through which we're injecting the flow. And if you look at the conditions here, we give it a velocity and a temperature that comes in, all right? And then with that, I'm just going to spend some time on chemistry here. So under reactions is where we have got all the reactions defined that I was just showing. The methane deforming reactions, and so on. And this is that discrete carbon reaction where it actually it's an amber alert. Okay, all right. So so this is actually what is capturing our carbon in here. Rate coefficients, and this is that discrete rate coefficient I was just showing the screenshot of. So it is all available here, many information about the units and so on. You can just directly copy paste this into your own reaction set if you need to. All right, with that, I'm just going to come over here. There are some basic time controls and so on, but in the interest of time, let me just click on Run Solver. As I said, the simulation is already set up for you to run. Now I happen to have one GPU on my machine, so I'm going to use it by clicking on this GPU panel. But if you don't have it, that's okay. You can uncheck this. If you have CPUs, you can use CPUs as well. All right, so let me just do this, and if I do this, it's going to start running the file right away from me. Okay, all right. I'm just gonna kill this here, and actually I have run this already, so I'm just gonna quickly show you some results before. Okay, so this is what I had in mind here. So if I were to open this guy, this is where I've already run. Imagine we go through the running down here, and then I go to this post-run option. This is where I find view results. And as you mentioned this, we use TechPlot for our post-processing purposes. But again, you see the simulation has been run till about 1800 seconds. I can look at quantities like my pressure in there. Obviously, this is isothermal, so the temperature is going to be uniform. But I could go ahead and load all my results files over time very easily. And let's say if I come in here and I'm going to plot my mole fraction of CO2 in this case. Right? This is what I was showing you. So you could start looking at the animation as well. I mean, I've only got a few files that are saved here every 20 seconds or so, but we can start playing around with it. All right. That's a short overview. Again, there are more details on the post-processing. One last thing I want to show you is, which is quite useful. And after that, I'm just gonna move back to the slide deck here. But imagine I want to set up a CFD simulation, right? But I want to use, for some reason, I like using some of the reactions that are available in this model. Do I have to manually type every reaction, every rate constant by looking at the post? No, I don't have to do that. In fact, I can directly import all the reactions from one project file or from one simulation into another simulation. So this, you can see, it's a totally different domain I have got in here, but my chemistry window is open down here. I don't have any reactions, I don't have any rate coefficients. And I want to use the reactions that I've defined in this SESMR project. So I'm going to come and say import materials and chemistry from another project. I'm going to say browse. Let me move into this SESMR we just looked at and load in the project file. And then it will ask me, do I want to import the materials? If I want to, but in this case I just want to import the chemistry. So I'm going to say import chemistry and append it. And that's it. Once I do that, you see that all the reactions, all the rate coefficients are available in this simulation. So you don't have to use our model. Maybe you only care about the chemistry that we're showing you in here. So download the file, get the chemistry into your model, and start using it. Okay. With that, let me just quickly jump back into my slide deck here. All right. So this example, I think like I said, we saw a great talk this morning about decarbonization of iron production. Or steel production. So I'm just going to briefly explain about what we have done in this particular application rather than go over the details. Again, as it was told this morning, a majority of the steel production is using this BF/BOF or blast furnace, oxygen furnace technology. It uses can use basically coke for combustion, so it's very very polluting in sense. So there's a lot of greenhouse gas emissions that come out of this process. And so there are several methodologies that people look at to sort of improve the or reduce these greenhouse gases coming from the production of steel here. One of those processes is what is known as the direct reduced iron shaft furnace or DRI shaft furnace. Again, just by switching over from a blast furnace to DRI shaft furnace, it is estimated that you can get the emissions down by about 50%. Now, essentially, it is a moving bed, and I'll explain that in a second. So you're injecting sort of your iron pellets, iron ore from the top. It's a counter current, so you're sort of introducing your reducing gas. And this is where the difference is, right? The reducing gas is not coming from combustion of coke. The reducing gas, which is primarily like CO and H2, it is coming from the outlet of a reformer. Right? Essentially, you have a reformer, and then it gets some CO, H2, as we looked at some steam methane reforming examples before. You take that reducing gas, and that is the reducing gas that you're actually using to reduce the iron ore to produce the steel. And this is a moving bed reactor. The iron pellets move down, so the gas moves up, and towards the bottom you collect your steel there. But what we have done is, in collaboration with Molten Industries, we've taken a step forward. We still aren't using this reducing gas, but the reducing gas is now primarily composed of hydrogen, essentially, and very little CO. So if we take the existing DRI shaft furnace and we use hydrogen as a reducing gas, more than 99% pure hydrogen as a reducing gas, we can reduce the emissions even further, up to 90%, which is exactly what this work is about. Like I said, this work's done in collaboration with Molten Industries. This is purely simulation work at this point. There's no plan built. But what we're doing is we took an existing published literature or domain for a Midrex DRI shaft furnace. For those who are familiar, Midrex has popularized the DRI shaft furnace work down there. So we took their shaft furnace example down here, and then we're trying to see if we can actually make it work with hydrogen in this simulation. Again, this is countercurrent, as I was showing you. Very, the hydrodynamics are important because this is a moving bed. This is not a fluidized bed. So, different kind of particle stresses are quite significant in this case, as you can imagine. And then particle conduction is also quite important to capture. So that the physics inherent in this are different, and we can actually model that within Barracuda as well. All right, so if I quickly move to the results here, the domain itself, this is the Midrex domain. This is the Midrex design for that. You basically are injecting iron ore feed from the top there. You have a reducing gas coming from the side. And then, basically, you also introduce some cooling gas from the bottom. The cooling gas is actually rich in methane. The idea is, as the iron ore moves down, gets reduced, you also want to cool it before you actually start getting, collecting it from the bottom. So that's why the cooling gas is injected in. But 90% of that cooling gas is actually vented out of this gas vent in the simulation. And then, like I said, okay, it's rich in hydrogen. The particles are uniform in this case, 15 millimeters. This is high residence times. We run these simulations for thousands of seconds. We run these simulations for about 20, 30 seconds worth of simulation time. Okay, this is important. This is sort of the initial condition of the domain before you run the simulation. So you basically have your magnetite or Fe2O3 on the top there. Then you have, I think you basically have the hematite and the woostite as well, which are the byproducts before you actually collect Fe from the bottom. So because this is generally how we expect the reduction to happen, you kind of initialize to get to a steady state solution quicker that way. Okay, again, one thing is we do have implemented a shrinking core model in this example, an unreactive shrinking core model from Hara. And again, if you go to our website, open the post, we have description for how this implementation has been done. You have your discrete reactions basically. These are all iron ore essentially reducing and getting Fe down here. So these are all discrete reactions that happen. In this case, because we are primarily using hydrogen, these are the discrete reactions which dominate. There's very little CO coming in. And then you also have some gas phase reactions which happen in the simulation. Oops. Okay, so what I'm showing here is actually, it's the same reactor. We are showing some slices, radial slices here. We are showing you firstly volume fraction, material volume fraction covered by each component down here, Fe2O3, Fe3O4, and then you have FeO essentially. All these three, you can see that as soon as Fe2O3 comes, it forms this byproduct. Eventually what happens is after these two byproducts, we just want to get Fe from here. But one interesting thing you're seeing is sort of this unreduced solids, right? These unreduced solids are actually making it down the reactor through the middle, the core of the reactor, essentially. Now, this is actually something that you observe mainly with using purely hydrogen as your reducing gas, because hydrogen is a lighter gas. So therefore what happens is, in fact, this is also observed experimentally by some researchers, where you start producing unreduced solids which are making way all the way down into your cooling zone, and you don't want that. So what we did is, in collaboration with Molten Industries, we actually increased the operating pressure. We made about 7 bar to prevent with that channeling effect. And so if you look at some quick results down here, what we're showing is, compared to the Midrex case, this new hydrogen shaft furnace, the CO2 emissions are down by about 97% by using almost pure hydrogen. In fact, the metallization rate, right, is comparable between the Midrex case and the hydrogen shaft furnace case. Comparable there. All right. Lastly, you can do a lot of what-if scenarios in this. Like I said, to just understand this unreduced solids problem moving down to the middle of the reactor. We have tested several flow rates here. Flow rates go from high to low. So you can see that as you increase the flow rates, you reduce the unreduced solids problem moving down. Similarly with temperature as well. But again, there are trade-offs, right? Higher temperature, higher flow rates means higher, gas compression costs or heating costs that you have to put upfront. So there has to be a trade-off here. And this is something that we're actively working with Molten Industries right now. Okay. With that, I'm going to move into the last topic today. This is the circulating fluidized bed combustor, which is the CFBC. If you are, I'm sure many of you are familiar here with the CFB, but I'm just going to go over it briefly. Essentially, what you're saying is that in a CFB, your furnace is a fluidized bed reactor. Right? So the furnace is a fluidized bed reactor. You are injecting basically primary air from the bottom here to a distributor plate, for example. You also are staging the introduction of your the oxidizer, so you have primary air coming from the bottom, and you can have multiple secondary air stages essentially to carry out the process of combustion in this reactor. Now the key advantage for a fluidized bed reactor, as we have been listening since the morning, is that you can essentially burn different types of fuel inside of it. That's the key advantage compared to a regular furnace. Inside of a CFB, it doesn't have to be coal, it could be biomass, it could be plastics, refuse fuel, or it could even be all sorts of junk that you can imagine. I've seen people put tires and other stuff as well. So it is fuel agnostic, as long as you can make sure that the fluidized bed is operating properly, which essentially means that you have a sort of a well-behaved circulating system, such that there's good mixing going on, which ensures no hot spots and even heat distribution. Once you do that, from a CFB, essentially there are various heat recovery points to recover the heat from the combustion process that can be used for power generation, so on and downstream of it. Okay, so again, fuel flexibility of a CFB over a conventional coal furnace, high combustion efficiency, and then the key aspect is you can achieve this combustion of coal and others at lower temperatures compared to a regular furnace. That actually means reducing NOx formation as well. And you can also throw in solvents to actually capture some of that sulfur pollutants that come out of this the CFB. Okay. In this particular case, what we have done is we have taken this model from work done by Yang. They were actually using biomass. We are happy to show this with coal in this particular example. Again, this is again, you not only have a fluidized bed reactor, you also have a couple of hydrocyclones in this case, and so therefore you want to get a detailed understanding and visualization inside of your CFB. So Barracuda and CFB solutions actually are quite ideal for that. You can understand not only basically the hydrodynamics of how your fluidized bed is behaving. You can start looking at the reactions that are happening inside, and any hot spots per se because of any skewed reactions that are happening, and so on. All these can be actually visualized. That's one other aspect we don't talk about enough in CFD, is the ability to visualize inside your reactor. That's not quite possible with many experimental setups, especially with reactions going on. So that is something you can do down here. And then once you do that, again, once you have a well-validated model, you can think about how to optimize it to reduce NOx, SOx emissions, and so on. Okay? So here is the domain here. I have got the CFB here. There's a primary air inlet, which is a plate on the bottom down here. I have got 4 coal inlets here, 2 on each side. And then I've also got 4 secondary air inlets on the top down here. And then the reactor side of things is a thermal wall BC. We have a wall temperature that we use on that particular side of the wall. As you can see, it's a real world domain. It's 500 megawatt geometry. It's 28 meters in tall. The width varies from the smallest section at 2.4 meters to about 5.4 meters. It is a compressible flow simulation with volumetric and discrete reactions. And there are some details about the flow rates coming in here. Okay, I want to take a little bit of time here and explain the reactions itself, because these tend to be quite similar when you look at any sort of coal combustion or biomass or plastics. Generally, the reactions and the kinetics can vary. There can be additional reactions that can come into, but you always have certain things which repeat. The first one is a drying step down here, especially if there's moisture in your feed. The first step that you want to do is moderate drying step. Then once it dries down, you have basically the pyrolysis of that feed that happens. So all these pyrolysis gases actually come out of your solid material that you're getting in. So that's actually the first thing that happens when the feed is brought in. And then you get like methane, CO2, some nitrogen-based compounds like ammonia and hydrogen cyanide and so on. Right? So this is the first thing that happens. Then you have simultaneously many other reactions happening. The volatiles that come out, then they start going with your oxidizer, right? The primary and this reactions start happening, and then you produce basically some CO2 and then hydrogen from that. So basically your volatile combustion is happening. Simultaneously, you also have some nitrogen chemistry which is happening inside a CFB. You have NOx formation that happens, which is, ideally you want to keep that as minimal as possible. but that, so what you do is you actually run this case basically, fuel rich, essentially, such that you can reduce your NOx emissions. Nevertheless, you do produce some NOx, and then if you do produce your NOx, the idea with this staged stage oxidizer index, secondary air index, is that you can reduce some of this NOx that is produced back into nitrogen or nitrous oxide and so on, right? So that's again, these reactions are not happening in isolation. They're all happening simultaneously, but I'm just breaking it down so you can understand that these are sort of the primary set of steps that happen inside the reactor here. Then you have char combustion. Obviously, when all the volatile gas released from the solid fuels, it's left with char. So you have char combustion and gasification reactions happen. You can also have further nitrogen chemistry where nitrogen can also, NOx reduction with char steps also take place. And then you also have additional char components which are solid sulfur, solid nitrogen, right? They can also be present, and some of those reactions are also can be used to model something like this. Lastly, sulfur capture. Again, like I said, this is one way to capture sulfur right in your reactor. You could use some calcium oxide essentially to capture some sulfur dioxide. We do try to do that inside this setup here. Okay. Very quickly, I'm going to walk through the animations here. What I've got here is several set of animations which are showing particles. Firstly, not all animations are showing all particles. We hide particles. We can only show the particles we want to in post-processing, so that is something to keep in mind. Firstly, I'm showing you ash circulation or devolatilized coal. This is important basically for good heat transfer. You see that that's happening inside the reactor. Then you also see basically your coal circulating along with your ash, right? So in this particular animation, I'm hiding ash and I'm only showing you coal. Now what happens is, it's hard to see, but this is basically, the particles are covered by mass fraction of volatiles here. So you'll see that a couple of red, few particles which are showing as red in color. So the particles come in with volatiles and immediately devolatilization happens, right? Very quickly, that is a very quick process that happens. And then what is left is, once the devolatilization happens, all you're left with in solid particles is basically carbon char. All right? And then not only that, now you can start looking at gas phase what happens to your gas phase reactions, right? So the volatiles come out, as you can see, you have methane, ammonia, HCN, but all these volatiles are getting quickly consumed. Most of the volatiles do not make it above the secondary air inlet down here. So this is actually showing transient results. We can also do time average results within Barracuda. So it's the same animation, but I'm showing you time average results, so you can very well see that none of those volatiles actually make it above the secondary air inlet from the time average results. Then I'm also going to show you quickly the CO2, H2, and NO production. In the interest of time, I'm going to keep it short down here, but again, you can see that all the oxygen that is coming in, that is basically getting or reacting with the volatiles that come out. Okay, and then you also have some NOx formation, but then there's also NOx reduction which is happening above the primary air inlet, and some of that actually goes towards water vapor, as you can see. Again, several of these insights that you can obtain from running these transient simulations, and then if I look at a time averaged image, some of these results become more obvious. All right, lastly, I'm just going to show you very quickly how ammonia profiling can be added to the CFBC. Now, again, I want to acknowledge this is work done not by CPFD. This is actually work done by Busan National University and KEPCO Research Institute out of Korea. I'm not sure if maybe some of the authors are actually present in the room here. This was actually work published very recently. This was only published in December 2025. Again, as I mentioned, there is a reduction mandate to reduce greenhouse gas emissions by 2030. As a part of that, the researchers in Korea are exploring is to see if you can actually use ammonia profiling along with the coal, right? And in this particular example, what the authors are trying to do is they are basically studying different percentages of ammonia profiling and trying to see and trying to find the sort of the optimum percentage that would actually help with CO2 reductions and even the sulfur pollutant reduction as well. All right. So again, advantage of CFD, we've already looked at that before. So key thing is, it is a CFD reactor. It is more of a smaller scale reactor, but the idea is the same. You have your fluid, your riser section down here. You have a hydrocyclone. The flow comes out. The key thing that they're looking at is, they have a primary air injector, a cold feeder. They also have a couple of secondary air injection points down here. Some of the details of the domain and so on are given. This slide deck will be made available so you can look at them. The key thing I want to point out is what they're doing is they're actually looking at different ammonia co-firing ratios, going from 0 to about 30%. And then, if you look at actually the chemistry in the paper, all these steps that I showed previously, right, whether that is the pyrolysis, the devolatilization step that happens, the char oxidations, the gas reactions, the reactions on the NOx formation, all of them are very similar in this paper. Now, the kinetics itself are different. They are obtained from their own sources, but all those steps are quite similar. In addition to that, what the authors mentioned is that if, essentially, so that's true. All of those steps are actually pretty similar. So that's why I don't have them down here. I strongly encourage you to look at the paper to see what reactions and what kinetics they have used. They've done a great job in providing all those details. So if you quickly look at the results down here, right, what I'm showing is 100% coal and 20% ammonia co-firing down here. We're looking at mole fractions of CO, CO2, H2O, and NO, right? I think the key aspect is to look at the mole fraction of CO2. If it's 100% coal down here, you can see that you're producing a lot more CO2, whereas when you start use ammonia co-firing, you can reduce some of that CO2. And because you're having more hydrogen atoms in the domain of ammonia, you actually end up producing more water vapor in the case. Right? And then what the authors have done is they've also given further information about the effect of that percentages. So they go from 100% coal to 10%, 20%, and 30%. And you can see that it's a pretty linear decrease in CO2 production. Where you go from 100 to about 30%, and you are CO2 mole fraction is decreasing along the height of the reactor. On the other hand, you're producing more and more H2O. Okay. With that, I think I come to a conclusion. I'll be more than happy to take any questions.
Thank you very much for a very impressive talk. This is the time maybe we only have time for one or two questions. Any questions from the floor?
Thank you very much for the nice talk. My name is Daejeon from Sunshine University. So the one question is that I am also working on the CO2 capture, but the presentation file is mainly based on the CO2 capture by the chemical reaction, right? However, in my case, my CO2 capture system is kind of a phase solution. That means the CO2 is sitting onto the surface, like by the other force.
Okay.
So in this case, I am thinking that if I would like to model this kind of thing, this is not a chemical reaction, but something kind of the equilibrium. So in that case, can I use this kind of thing as well using this Barracuda or other conventional you have?
So deposition on particles is something that you can model within Barracuda. Now,
exactly.
How that deposition happens, as you said, can vary. It can be through some sort of a chemical reaction, or maybe some other conditions for the deposition. But to model, yes, you can model. In fact, deposition happens and particle sizes actually grow. Particles actually grow in size because of that deposition. So that is something that can be modeled within Barracuda. Maybe we can talk more about it to see how exactly you want to implement that. Again, maybe we have to implement it through a user-defined way, but just to know that deposition is accounted for and can be modeled within Barracuda on solid particles.
Okay, let's talk about later. Thank you so much.
Let's start with the speaker and let's have some break.